Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the shear stress distribution of I section. The course outcome related to this session is apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stress, shear stress distributions and failure of beam sections. The Bloom's taxonomy level related to this topic is apply level. This is the I section. It is a symmetrical about both x-axis and y-axis. It is a symmetrical axis. Figure A indicates I section and figure B indicates the variation of the shear stress across the flanges, top and bottom flanges, and also at the web section. This is the variation at the top flange and the variation at the bottom flange. At the section, it is varying parabolically. The maximum shear stress occurs where, here it is, the neutral axis. At neutral axis, it is observed as the maximum shear stress. Now, let us describe the figure A. The figure A consists of the way capital D is the overall depth of the section, capital B is the overall width of the section, and small b is the thickness of the web, and small d is the depth of the web. Now, the shear stress variation at a distance y from neutral axis at any section is given by the formula we already derived in previous sessions, that is tau equal to F Ay bar by Ib. Now, for this section, in this case of the I section, there are two parts are there. One is flange, another one is web. So, we are going to find out, we have to find separately the web and shear stress, the shear stress distribution in the web and the shear stress distribution in the flanges are to be calculated separately. Now we are going to find out the shear stress distribution or variation of the shear stress. First, in the flange, how we are going to find out? Consider the shaded area is at a distance y from neutral axis, as we have followed in previous sessions, that is rectangular section and circular section. So from neutral axis, the overall depth that becomes d by 2 to the topmost flange, and the inside the web distance, the depth of the web, that is d by 2. Now, what to be needed here? We need A y bar. What is the area of this shaded area, and also bar y? What is the bar y? That is the centroidal of the shaded area, distance of centroid of the shaded area from the neutral axis. Now, consider, yes, we considered a section at a distance y from neutral axis in the flange. Now, width of the section, that is what is the width of the section is capital B of the flange, and width of the section, width of the web is small b. Now, shaded area of the flange, that is equal to this, the V is the width, B minus B times d by 2 minus y, that is d by 2 minus y. This is the shaded area, and that is the area, but here capital B times, there are two portions are here, very important. Here one more is that d by 2 minus small d by 2 plus another portion is this, the portion. What is that portion? D by 2 minus y times small b. That is the total shaded area. But we want here shaded area of flange portion. The shaded area of the flange portion is, this is the portion, shaded area of the flange portion. That is width, even though we calculated, this is a small letter. The shaded area of the flange portion, here it is, small letter b times shaded area of the flange portion, that is b times small d by 2 minus y. This is the v is the small b and d by 2 minus y. This is the shaded area of the flange portion. We got it. But another shaded area is here. The shaded area of a flange portion. Wait. The shaded area of the flange portion is correct. That is b is the width times d by 2. B is the width times capital D by 2 minus small d by 2. But the complete shaded area we want, then what will happen here, it is complete shaded area, that A equal to, this is the shaded area of a flange and shaded area of the web also there. Then the total shaded area, total A equal to plus small b times d by 2 minus y. This is the total. Next, what is the bar y? The bar y equal to y plus half of d by 2 minus y, capital D by 2 minus y. So then the bar y comes half of d by 2, 1 by capital D by 2 plus y. Now this is the shaded area we found bar y from the centroid, that is from neutral axis. Now shaded area, hence the shear stress in the flange becomes, that is F Ay bar by Ib, F times B times d by 2 area d by 2 minus y plus half of d by 2 plus y bar y, that is Ib. Now this is the equation F by 2I times d square by 2 minus y square, that is the d square by 4 minus y square. Here the variation of the shear stress with respect to y in the flange is parabolic. So it is from that equation, we understood from the equation, that is the equation 1, that the width, when as y increases, the shear stress decreases and vice versa. So we want at upper edge of the flange, then y equal to d by 2. If you substitute y equal to d by 2, where y equal to upper edge of the flange, then it becomes, shear stress becomes 0. That is F by 2a times d square by 4 minus y square. The shear stress becomes 0. Yet y equal to 0, the shear stress is observed as maximum. The maximum, yes, at y equal to, yes, we want at this edge. At this edge we want, that is y equal to d by 2. At y equal to d by 2, substitute small y, then it becomes y equal to d by 2 f by 2a times capital D square minus small d square by 4. That is f by 8a times capital D square minus small d square. So it is a constant here. That's why it's constantly suddenly increasing. That is, there are two portions which we have studied. Part 1 for upper edge of the flange and part 2 and at the distance of d by 2. First we have calculated shear stress distribution in the flange. The next one is shear stress distribution in the web. This figure indicates the complete shaded area of both flange and web. Now we want in the web. The web portion, how it comes? We want, then web portion means flange plus web. We want in the web portion, before we calculated in the flange portion. Now in the web portion, what is the area? We want AY bar. What is the AY bar? The width of the section, web section is B, and the width of the flange section is capital B. So AY bar means moment of inertia of a flange area about AY bar, total moment of inertia, the moment of inertia of the flange area about neutral axis plus moment of shaded area of the web about neutral axis. Then what is that area? We are going to AY bar directly. We are going to calculate here. That is B into capital B into A, that is capital D by 2 minus small d by 2. This is the zone into bar Y. What is the bar Y? Y bar is 1 by 2 times capital D plus small d by 2 plus, that is a moment of area, a moment of the flange area about neutral axis. About neutral axis means here it is, yes, 1 by 2 times d by 2 plus d by 2 plus we want web. The web is, what is the area? Small d by 2 minus y. That is b times area d by 2 minus y into bar y. What is the bar y? Here it is. This is the portion we want, bar y. The bar y means from the distance from here to here. That is d by 2 minus y. And we want this portion, d by 2 minus y. D by 2 minus y means this is the, what is this distance? This is the y distance. This distance is d by 2 minus y distance. We want from here to here. Let me wait. Yes. That distance comes bar y of the flange, bar y of the shaded area of the web, bar y portion comes y plus, this is the y portion, y plus this distance, that is d by 2 minus y by 2, half of d by 2 minus y. Then if we simplify it here, y plus d by 4 minus y by 2. Then it becomes y minus y by 2 plus d by 4. Make it common here, 1 by 2. Then what will happen? 1 by 2 times y plus d by 2. This is what? Y plus d by 2. 1 by 2 times y plus d by 2 or d by 2 plus y. Suppose if we want the distance, how this term we got it? We want this term, that is the bar y of y bar or bar y of flange from neutral axis. This is the distance we want. How it comes again? That is y1 bar, that is a flange term. So this term comes here to here, d by 2 plus half of this portion. So d by 2, that is flange y bar equal d by 2 plus half of this portion means the difference between this portion we want, this shaded area. This area is d by 2 minus d by 2, capital D by 2 minus small d by 2. Half of that, 1 by 2. If we simplify this, what will happen here? D by 2 plus small d by 2 plus capital D by 4 minus small d by 4. So this d by 2 off, that means that is a d by 4, half of that mean, plus d by 4. So if we make it common 1 by 2, that is capital D by 2 plus small d by 2. This is the term obtained like that. After substituting, now ay bar, after substituting the value of in terms of capital D and small d, bar ay bar, area and bar y, then simplification, if you simplify it, then it comes, the value equation becomes b by 8 times capital D square minus small d square plus b by 2 times d square by 4 minus y square. Hence, the shear stress in the web becomes as, substitute here, F A y bar by IB. This A y bar means this is the value. Then F by IB times A y bar, B by 8 times capital D square and small d square plus B by 2 times D square by 4 minus y square. Now, this is the shear stress variation in the web, equation of web. Now, if we want at different places as the shear stress varying along with y, the shear stress variation of the shear stress with respect to y, the y is the variable, the distance from neutral axis, where capital D, the values of B, width of the overall width of the I section, capital D, overall depth of the I section, small b, depth of the web, and small d is the depth, small b is the width of the web. All are constants, geometric properties or geometry dimensions of I section which are constant. The variation of the shear stress here, it is only along with y variation. It varies along with y. So the shear stress is varying the square of the y. That means it is varying parabolically, non-linear, quadratic function. So the variation of the shear stress in the web portion is constant everywhere in the web portion, and the flange area also, shaded area also, it is parabolically varying. Now, wherever, if y equal to 0, what is the shear stress? So as y increases, the shear stress decreases, and as y decreases, the shear stress increases. Now, at the neutral axis, what is the value of the y? The value of the y at the neutral axis is 0. Substitute at value of the y equal to 0 in this equation, then value of the y equal to 0 in that equation, then the shear stress, the maximum shear stress is observed. That value, that equation is F by IB times B, capital B times capital D square minus small d square by 8 plus BD square by 8. This is the tau maximum. Now we want at y equal to small d by 2 and y equal to capital D by 2. If you substitute at y equal to small d by 2 in the above equation, again the equation y equal to small d by 2, then that equation, the shear stress will be at the junction or at the junction of the top of the web and the bottom of flange. That is called web, at the junction. What is the junction here? It is I section. This is the junction portion. The bottom of the flange, top of the web from neutral axis. This is the portion d by 2. Y equal to d by 2. If you substitute y equal to d by 2, then the formula is transformed into another way, another type here, that is f tau equal to f b times capital D square small d square by 8 IB. Now we want at the extreme, at the top of the flange, substitute small y equal to capital D by 2. Then you can observe it. What is the variation of the shear stress at the top of the flange? So in that manner, we can observe the variation of the shear stress along or across the section of the beam. Here the section of the beam is I section. The beam can be a cantilevered, the beam can be a simply supported, and the beam can be a overhanging beam. And also the beam can be a fixed beam. But the section of the beam is I section. Along the section of the beam, along the length, not along the length of the beam, along the section of the beam, how the shear stress is being varied. By using this relation, we can calculate the value of the shear stress. In this proof, in this derivation, we found at two portions we have calculated the shear stress distribution in the flange and the shear stress distribution in the web. So we can understand the application of this derived formula while solving the problems. So this is the problem we considered to calculate the maximum shear stress developed in the I section. So here it is the I section having the overall width of the section is 150 millimeters, overall depth of the section is 350 millimeters, the depth of the web is 310 millimeters, and the width of the web is 10 millimeters. And the thickness of the flanges are equal at the bottom and top flanges, that is 20 millimeters. The width and thickness of the flanges here, bottom and top flange, are 150 millimeters and 20 millimeters. So an I section beam, it is 350 by 150 millimeters, has a web thickness of 10 millimeters and a flange thickness of 20 millimeters. If the shear force acting on the section is 40 kilonewtons, that is the F value, 40 kilonewtons, find the maximum shear stress developed in the I section. Only single objective. Okay. Now data was given here. The given data, capital D overall depth, capital B overall width, and B web width of the web, that is 20 mm, that the flange thickness is 20 millimeter, top and bottom flanges. What is the depth of the web? That is 310 millimeters. The depth of the web is 350 minus 2 times flange thickness. 350 minus 2 times 20, 40. 350 minus 40, that is 310 millimeters. This is D. This is capital D. 150 capital B. This is small b. Now, the shear force on the section is given, that is F equal to 40 kilonewtons, that is 40,000 newtons. Converted kilonewtons into newtons, that is 40,000 newtons. Now, we want moment of inertia because we know the formula, the generic formula, that is for I section, the formula just now derived, that is F by IB times B time capital B times capital D square and small d square by 8 plus BD square by 8. This is the I value. How to calculate that I value? We know the I values. Consider here, we considered this is completely closed. This is one rectangle minus 2 times small rectangles, this zone. Then we will get it the I section. So outside this is BD cube by 12, 150 times 350 cube by 12 minus, subtract this portion. What is this portion? Subtract this portion. The depth is 20. What about width here? What is this zone? So here it is 150 minus 10, that is 140. The shaded area of the thickness, the width is 150 minus 10, that is 140. So BD cube, B is here 140, D is here 310. So 140 times 310 cube by 12. If you subtract, then this portion will come, that is I section portion. So that is about neutral axis. The calculated value of the I here, it is 188375833.4 millimeter per 4. That is the I section. Now we know the maximum shear stress value, that is equation for maximum shear stress for I section. We derived before that F by tau maximum shear stress equal to F by IB times B, capital letter D square minus small d square by 8 plus BD square by 8. Here substitute capital B equal to 150, capital D is 350, small d 310, small b 10 millimeters, I value calculated. All these known values substitute here in this problem. Then the maximum shear stress is observed as, here it is 13.06 Newton per square millimeter. The maximum shear stress. Now the maximum stress value, here it is, that is 13.06 Newton per square millimeter. Here one more thing is that it is not asked. Suppose asked here at the junction of the web, and flange, find out the shear stress variation. Then we have to substitute F value and B, FB, capital D square, FB by 8 IB times capital D square minus small d square. FB by 8 IB times capital D square minus small d square. This is where at the junction. Where is the junction? Here it is the junction. How it varies. So what is the F value here? The F value is, that is, what is the given here? F value, FB by 8 IB. FB by 8 IB times capital D square minus small d square. The F value here it is 40,000 newtons. Capital B value 150. 8I 375,833.4. What is the B value? 10. Capital D 350 square minus small d 310 square. So after substituting these values, we can calculate the variation of the shear stress at the junction. The variation of the shear stress at the junction we have calculated of substitution. This value gives the junction value. And suppose if they asked you the shear stress variation at the neutral axis, the shear stress variation at the neutral axis, then the formula, where it is the neutral axis, at the neutral axis at y equal to 0, that is the maximum shear stress. F by IB times B, capital B, D square minus small d square by 8 plus BD square by 8. This is the variation, that is at y equal to 0, that is the maximum shear stress. So thus we can calculate the maximum shear stress and also the shear stress, the maximum shear stress value, and also the shear stress at the junction. Okay. Now for different I sections, here the I section is symmetrical about neutral axis. The I section is symmetrical about x axis and also y axis. It is the complete symmetrical axis. It is symmetrical about both x axis and y axis. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.